Okay, now we are looking at homework 12.2. In this problem, we're given mole fractions, and we want to try and find mass fractions. So the mole fractions for each, let's make a table again with the gases. So the gases, and this time the mole fractions. And I've got CO2, same gases. It may even be the reverse numbers. H2O. And we're also given the temperature and the pressure of the mixture. The mole fractions are given as 0.15, 0.44, 0.31, and 0.1, and the sum of those all need to add to 1. So we have, we got them all up, we get 0.5, 0.05, 0.04, 0.01, 0.00, which is then 0.1, so we carry the 1, and we have 2 plus 4, 6, plus 3, 9, plus 1, so we have equals 1. So we add that all up, get 1, so we know we have all the gases, and now we're trying to find the mixture molecular weight. So again, with mole fractions, ultimately here we're going to try and find mass fractions. I'm not going to derive this one. This one is a little easier, but the mixture molecular weight turns out we can get that by doing the sum of yi mi. And you might guess that we can get the mass fraction I as before we had that term for one of the components over the sum, and turns out it's the same format here. So we have yi mi over summation yi mi. And so if we were trying to find the mass fraction for CO2, it would simply be yi, or y of CO2, times the molecular weight of CO2 over the summation of all of them. So y of CO2 plus, rather, times molecular weight of CO2 well, let's write it not as a sum, plus y of N2, molecular weight of N2, plus y of O2, molecular weight of O2, plus y of H2O, molecular weight of H2O. And then we do that for each one. Of course, the denominator all being the same. The denominator then is the molecular weight for the mixture. So it might be worth writing, let's put that in one column over. Let's put mi in a column. And we have 44.01, 28.01, 32, and 18.02. And then this next column we could put yi mi if we wanted to calculate it here. So 0.15 times 44. 0.15 times 44.01, and 0.44 times 28.01, and so forth. Do that for the others. And then we'd sum all those up, and that would give us the mixture molecular weight. And finally, this equation that we have here, which is the first one, we can have mass fraction of I, which then would just be this value divided by the sum. So then we have yi, well, in this case actually y CO2 mCO2 over the molecular weight for the mixture. So let's try this. Instead of doing it here on the board and doing it by hand and punching in the calculator, let's try this in a table on the computer. So if I use, say, a spreadsheet to do this, I can write a program to do this. But let's try a spreadsheet. So and I'm going to make a column called gas, yi, capital MI, do my yi mi column, and then my mass fraction. And then my gases are CO2, N2, O2, H2O, and 0.15, 0.44, 0.31, and 0.1. And the molecular weight's 44.01, 28.01, 32, and 18.02. And then now I just simply multiply this times this, so that's my yi mi, and then that's the same equation for each of those. And then I'm going to sum those. So equals, let's put that over to the right here, and equals sum of all these. So that's my mixture molecular weight. And then this equals this number divided by yi mi divided by the sum of yi mi. And that cell I want to lock, so I'm going to hit F4 so that cell doesn't move when I copy the formula. And then I copy this down, and each one of these always refers to this bottom cell then. And those are my mass fractions. And then I can go back, let's shrink this down a little bit and just check our answers. So I've got the mixture molecular weight should be 30.648, and I've got 30.648. And then my CO2 is 0.215, and 0.215, my N2 0.4021, my O2 0.3237, and my H2O 0.0588. So now I've got a little program, if you will, or spreadsheet that calculates this. The only thing I don't have here is the specific volume. So I'm going to write PV equals MRT. So I'm going to use this equation. And I'm trying to find the specific volume, so let's actually write this as PV times RT, or equals RT, so that would be volume divided by mass, the specific volume. So finally then I get right down here, so V equals RT divided by P times, or just divided by P. Okay, and then put that here. So I need a few things. I need the temperature, I need R, and I need the pressure. So we come for this. those values in here. The temperature is 418. It's in absolute temperature, so that's good. R equals 8.314 kilojoules per kilogram Kelvin. So if I divide R bar by the mixture molecular weight, I will have the gas constant, 0.2745, and then the pressure is 1.18 bar. So that's in bar. I need it in kPa, so let's put that as bar, or we can just, that'll work, pressure in kPa, and that would be this number times 100. And then finally, let's separate this so I know it's calculated. I can, no, that's fine. Then I'll have equals R times T divided by P. I'm going to put it so that it's in bar, so all my units are kPa, so all my units work out. Of course, alternatively, I could have multiplied that times 100. And I get a different answer. So let me see what I did in error here. Okay, so I found my mistake. Taking a little closer look, everything looks good, except I assumed this was degrees K or Kelvin because it looked like a large number, but in fact that was in C. And so let me do the same thing. Temperature Kelvin equals this plus 273.15. So now my equation should use temperature in Kelvin. And when I do that, get a little better answer, 1.6078 and 1.589. Let's experiment a little bit. Don't think it's going to depend on that. Okay, it took me a little time here, but found my other mistake. I meant to type 8.314 and I typed 8.413. So 8.314. So my gas universal gas constant isn't so universal today. Let's do that, and I get 1.589. So here's a good illustration. I'd like to say I did this on purpose, but I didn't. But whenever you do problems, you're probably going to make some mistakes, especially if you're trying to do it in a hurry, like on a video. And so when you write a program and then you have some values that you can trust, maybe some calculations that you've carefully checked, and now you're writing a program to make sure your program's right. The advantage of doing this then is, now that I know that all my values are verified, if I were to, say, change this to 520 degrees C and a pressure of 1.45 bar, I'm very confident that these values are correct. And if I changed my fractions, let's say this went to 0.33 and 0.21, and then I might want to equals some of these to verify that in fact I have equal to 1. So if I do 1, now they all sum up to 1, so those mole fractions, I have a little check on that. Maybe my mass fractions, I should do the same. It's another check that everything's good. And now I've got something, I can do any problem with these 4 gases, different mole fractions, different temperatures, different pressures. If I don't like this idea of having K and kPa in here, then I just build it into my equation. So I would say temperature plus 273.15, And then if the pressure is always going to be given in bar, times 100, and then move this to bar, move this to degree C. And let's go back to the one we had just to verify. So I've got 418. I don't need this anymore. And I don't need this anymore. And 1.18. And let's go back to 0.15, 0.44, 0.31, and 0.1. And I get all the correct values. Can clean this up a little bit. Now I have a nice utility to do homework 9.2.